It's really my greatest pleasure to introduce today's speaker, Professor Matt Reynolds. Matt joined this department in fall 2013. We kind of steal from Duke University, one of the superstars in the area of ultra-low power sensing, computation, RFID, and power transfer area, especially applied to biomedical application. And we are really lucky to have Matt join this department. And he got his bachelor, master, and PhD degree from MIT. And after that, he joined Duke University and became an associate professor. Now he's coming to UWEE to start a new career here. In his past couple of years, he has more than 3 patents and more than 14, right?
3 companies.
Right. 3 companies and tens of the patents and also 5 best paper awards in this area. So that's really an impressive record. So let's welcome Matt to give us a very wonderful talk.
Thank you, Jen Neng. I'm very happy to be here and to speak to you. I see a lot of friends and students in the audience, so it's great to have this opportunity to speak with you. Today I'm going to be speaking about wireless power, and the title of the talk is Challenges and Opportunities in Wireless Power. It's an interdisciplinary field with a lot of promise, and there's a lot of consumer demand for wirelessly powered products, but there are also some technical challenges that I'd like to highlight. The first thing I'd like to say is that wireless power is not a new idea. It's a very old idea that has been around since the dawn of the electric power industry. So if you think back to 1882, Edison had his Pearl Street electric generating station in New York City. And in 1882, he had about 10,000 light bulbs wired up in New York City. And a last mile problem came up. How are you going to wire all of the other buildings in New York City? And that was a big challenge. And Nikola Tesla thought he had the right answer. So you can see this headline from the New York Times in 1898. To transmit electric power, Tesla claims to have solved the problem. He'll just send it through the air. And that idea became a big deal. You can see this other article from the early 1900s. Also about Tesla, and the title of it is Cloud-Borne Electric Wavelets to Encircle the Globe. And that word wavelet probably means something different in 1904 than it means today. But my point is that wireless power is a very old idea, and there's been a demand for it for a very long time. In terms of application domains, this is another case where what's old is new. Obviously, people are very interested in wireless power for recharging electric vehicles. But that problem has also been around for a long time. So here's Jay Leno. You may know that he's a very serious car collector. And the car that he's working on here, driving and working on here, is a 1909 Baker Electric. And it's an all-electric car. It runs on lead-acid batteries, which Jay has got right there. And this car had a range of about 110 miles on those lead-acid batteries. Well, you fast forward about 100 years, and you've got a Tesla with a range of about 260 miles. So 100 years of progress in electric vehicles, and you've got only about a doubling in range. So recharging those batteries is a big deal to extending the range of electric vehicles. Also, you look at mobile computing as an application area. And the iPhone 5 that you see here is about 50% battery by volume. So wireless power is interesting because it has the potential to keep those batteries recharged over a long period of time, so you're not going back to a wall outlet every day to recharge your phone. Now, I would say that in some ways, wireless power is already here. These are RFID tags, passive RFID tags. They get all of their operating power from the incident radio frequency signal. And this is an area that I started working on in industry about 15 years ago. And since that time, it's grown from research technology to an area, an active business with about 6 billion tags per year. So I would look at this as 6 billion wirelessly powered computers being made and sold each year. And really the potential is there to have a far greater deployability of wirelessly powered computers as more capabilities can be added to these small systems. This plot over here shows the growth in energy efficiency of computing over time. So the x-axis is time, and the y-axis is computations per kilowatt hour. And you can see that we're on a good trend. The energy per computation has decreased dramatically over the last few decades. There's some argument about how we're going to continue that rate of progress as we come to the end of Dennard scaling, but still the trend is there. There's also plenty of room, by the way. Today, these best, most energy efficient systems are consuming on the order of 3.6 times 10 to the minus 10 joules per computation, and the Landauer limit's on the order of 10 to the minus 21. So there are many orders of magnitude of potential improvement. The question is, how do we get there? It will probably come from alternative computing technologies. So in addition to mobile and wireless computing, wireless power can also enable new application domains like space solar power, which has been talked about for about 40 years now. The idea being gathering solar energy out in space where there's no attenuation from the atmosphere, and you could have a very large collecting area, and then beam power down with microwaves to a receiving station on the Earth. And one of the pioneers in that area is this guy Brown, who in the 1960s did a couple of important demonstrations of wireless power, including flying this wirelessly powered helicopter back in 1964, and demonstrating at the Goldstone radio telescope transmission of wireless power at the 30 kilowatt level over a kilometer of distance and about 84% efficiency. We have here at UW some very promising new work that Josh Smith's group is doing in harvesting energy from ambient sources. In these cases, there's an external source of RF power, which is coming from some infrastructure. Josh's work takes advantage of the realization that there already is a lot of transmitting infrastructure in the world. In particular, these are the digital television transmitters on Capitol Hill. And they're radiating about 1 megawatt of effective radiated power all over the Seattle area. So the idea is that if you're trying to power something very small, perhaps you can capture just a tiny fraction of that 1 megawatt and use it to run some kind of local device. So there are new application domains enabled by wireless power. I have an example of that in my lab, which is providing power to biomedical sensing devices or biopotential sensing devices. This is a dragonfly, which is a very small animal, weighs about 130 milligrams, and it's carrying a wirelessly powered telemetry backpack. And obviously with an animal as small as 130 milligrams, we can't afford the weight of a battery. So we have to beam the power in with a radio signal, which is picked up on this dipole antenna and is used to power the backpack. So, looking at this very broadly, there's a bunch of exciting application domains, and the question is, what technologies can we use to address those application domains? I kind of divide the world of wirelessly powered devices into groups, low and high power groups, where the low power groups are things like mobile device charging or implanted devices or perhaps RFID systems in the microwatt to watt range. And then there are also high power applications like recharging electric vehicles or potentially charging autonomous flying vehicles in flight. These are applications in the domain of watts to kilowatts, primarily because they're not so focused on energy for computation, they're focused on energy for locomotion. At the same time, we have some distinction in terms of range. Some of these systems can be useful at short ranges. Others require long-range communication. And this distinction between high and low power and long and short range drives you into different technology domains to address those problems. The short range, particularly high power applications, are usually addressed with magnetic induction or coupled magnetic dipoles, as I'll describe to you in a moment. This is transfer of energy in a coupled magnetic field from a source to a receiver. Some of the long-range applications are addressed with electromagnetic waves, like the RFID tags that we saw before, or the Dragonfly, or other applications like that. And these two distinct modalities for wireless power have distinct physics. that drives the design of the system. And that's what we're going to talk about in this talk. So I'll start with a brief overview of wireless power and what those physical modalities for power transfer are. We'll talk about a couple of applications from the lab, neural recording in the flying dragonflies as an example of a system that can only work with wireless power. I'll also talk about transferring power inside a multipath environment in a building, like an office building or a lab or another place like that, using MIMO techniques. MIMO, you may know from communication systems as multi-input, multi-output. Right? We're taking kind of a different view of MIMO to apply it to energy transfer as opposed to communication, and I'll talk about that distinction as well. Then finally, I'll talk about some joint work that we've done with Toyota in near-field wireless power focusing for recharging electric vehicles. So that's in the short-range, high-power case. And I'll give you some concluding thoughts about where this field might go. So here's a brief overview of wireless power transfer. The idea is that we have some source transferring power to some load through a two-port linear network. And the idea is I've lumped the transfer modality and the antenna system together into this two-port linear network. And I'm driving it with energy from some source. For example, this might be from a wall plug connected to a transmitter. And then I've got some load where I'm going to accept the energy and use it to do useful work. And this linear network, regardless of the modality, it could be a coupled electric field, could be coupled magnetic field, could be electromagnetic wave propagation. They're all examples of some kind of coupled linear network. And if you have a network like this, you can understand the efficiency in terms of the power delivered to the load divided by the power available from the source. And there's an expression right here which highlights many of the challenges that we're working on actively. This expression is not a simple one. It depends on impedance matching between the source and the linear network, and then between the linear network and the load. And the idea is that if all of these ports are matched, we have some efficiency, which is the magnitude of S21 squared. But if those ports are mismatched, we have to consider that mismatch in the efficiency calculation. Impedance matching is a very important problem in wireless power. Now, how is that linear network made? It could be made of some near-field modality like coupled magnetic dipoles. And in that case, the mutual coupling between two magnetic dipoles goes as 1 over d to the 6th. So that's the dominating factor in the efficiency. Or it could be a far-field modality like coupled electromagnetic waves, the familiar 1 over d squared. But in both cases, regardless of the modality, the idea is that the power that's available is decreasing as a function of distance. And we'd like to mitigate that as much as possible. That's what some of the research I'm going to talk about is about, mitigating that decrease in efficiency as a function of distance. But it comes down to the fundamentals of the coupling between the source and the load. Now, there's a couple of research challenges that are active, and my group and Josh's group and other groups are actively working on these. One of the main challenges that we face is that real systems have nonlinearities. In other words, the source and the load in particular are not linear networks. We're trying to transfer power through a linear system made up of the antennas and the wireless channel, but we have to drive them with nonlinear devices. And an example on the source side would be converting from grid power to some radio frequency signal. That requires an oscillator and a power amplifier. This thing is fundamentally a nonlinear device that has to be matched to a linear network. And then on the load side, we have some rectifier which converts an incoming radio frequency signal into DC power, let's say, to drive the load. And that's a nonlinear device too. I see some of my students from UWEE 332. You're familiar with the diode equation. This is a nonlinear equation. So if we're trying to couple power from this linear network into the nonlinear load, we have an impedance matching problem immediately. And that varies dramatically with motion in the system. If you move the source and the receiver away from each other, that linear network changes. And as a result of that change, all of the matching conditions at the input and the output will also change. So that's a big challenge that has to be solved through research. A second challenge is efficiency at low input power. So if you examine the case that Josh Smith's group is doing, where you're trying to harvest power from ambient sources in the environment, your source is a megawatt class device, but at the receiver, you're looking to power something very small. You have only, let's say, microwatts of power available to you. And at those low power levels, you also have a low incident RF voltage. And the problem with low incident RF voltages is that you sit in the very shallow part of the diode's IV curve. And so the diode's rectifying efficiency is much lower at low input power. And this is kind of a bit of a curse. You'd like to have high efficiency when you only have a small amount of energy available, but that's not what the diode does for you. So I've plotted over here several different harvesters that we've built in our lab and a couple of the results from the literature. We see efficiency in the rectifier on the order of 80 or 90% at incident power at a milliwatt or above. This is the regime that Brown demonstrated back in the 60s, very high efficiency at high input power. But as you get lower and lower and lower incident power, the efficiency takes a nosedive due to the nonlinear behavior of the diode. And so kind of addressing or mitigating that problem is a significant area of research. And I would say it in this way, these low power systems are both power limited and then also voltage limited. Both from the perspective of the rectifier, they're limited by the voltage across the diode, and then also in terms of the DC voltage that's delivered to the load. Perhaps you're only delivering millivolts of voltage to the load. You have to convert that to some useful voltage. A third challenge is achieving high efficiency over wide bandwidths. And if you look at the matching from the source to the wireless channel and from the wireless channel to the load, you have impedance matching challenges at both of these boundaries or interfaces between these networks. And if you just imagine the load to channel case, you have some load impedance looking into the load and some source impedance looking into this linear network. Maintaining a matched condition for those loads over widely varying frequencies is a significant challenge. In wireless power systems where you control both ends of the system, you can design everything together and say, okay, I'm going to work at a particular frequency all the way through. But if you're trying to harvest ambient power, you have to take advantage of the power that's available in the environment. For example, the television transmitter frequency is set by the TV guys and the FCC. It's not something that you can change. And so one of the recent innovations that I'd like to highlight, actually, Aaron Parks and Josh Smith's paper won a Best Paper Award at IEEE RFID this year, is basically a multi-band matching network. So they've developed a set of matching networks that deliver good impedance matching over a wide bandwidth by segmenting the frequency spectrum up into different bands. And you can see that here in a block diagram form. And then also you see the different band harvesters all connected together here in the physical implementation. So that's an exciting research contribution from Josh's group. And I think there are other areas where this problem can be addressed as well. Then finally, a fourth challenge is human safety. People often ask me, well, if you're transmitting power from one place to another, are you just cooking everything in between? That is true in the limit. You would not want to stand in front of the Goldstone dish while it's transmitting 30 kilowatts of power. That would be bad news. But the good news is that we have a human safety regime in the United States, and it's based on a combination of frequency and power density. And this is a plot from the FCC's regulations for human safety in the presence of electromagnetic fields. And the idea is that at each frequency, there's some allowable power density, which varies as a function of frequency. So here's frequency on the x-axis and allowable power density on the y-axis. This limit varies as a function of frequency. Generally speaking, at lower frequencies, you can tolerate higher power densities. That's due to the biology of the system. And this is where things like electric toothbrush chargers and most of the wireless vehicle chargers work. If you're trying to transfer kilowatts of power, you do it in a regime where you can tolerate a high power density. On the other hand, if you're looking for power harvested from, let's say, a television transmitter at several hundred megahertz, that's out in this frequency regime over here. Lower power densities, but the propagation characteristics of those high frequencies are favorable. So there's a lot of challenges going on that have to be kind of simultaneously dealt with in the design of the system. And I'll take you through a couple of examples of how we're trying to push on those challenges to achieve better results in particular situations. The first one that I'll highlight is the Dragonfly system, where we have to be battery-free to the extreme. We couldn't tolerate a battery at all due to weight in that case. And this is joint work. My collaborators are Anthony Leonardo from HHMI Janelia Farm, which is a neuroscience research center, and Reed Harrison from Intan Technologies in LA. He designs neural recording chips. This problem is an interesting one. It's a science problem. We're trying to address a fundamental science problem of understanding how the dragonfly updates its wing steering to maintain an interception course when catching prey. And in order to do that, we're recording from certain neurons in the dragonfly. And these are these neurons called target selective descending neurons. And they fire in response to input from the visual system of the dragonfly, and they're implicated in control of the wing steering. So we're trying to record from these neurons in flight to understand this control system that's part of the animal. But in order to do that, we face a lot of physical challenges. We have a very small animal with a very limited payload capability. We've addressed that payload capability issue by wirelessly transferring the power in instead of having a large battery. And we're using a 900 megahertz radio signal to do that. By wirelessly transferring the power in, we're able to achieve very low package weight because there's no battery. There's also very few other supporting components for the device. So I would look at this as a wirelessly powered system, right? It's battery-free. We're transferring power in, and we're getting data out from the Dragonfly. And the data that's coming out from the Dragonfly is kind of a Wi-Fi class data rate from a package that's only a few square millimeters in size and has a weight less than a postage stamp. Now, we're able to do that because of the low-power communication technology called modulated backscatter. This is a plot of data rate versus power consumption for the communication side of the equation. Here's conventional wireless systems, Wi-Fi, Bluetooth, and so forth, up in the 10 nanojoule per bit range. The backscatter communication modality allows us to do the comms part of the system in only a few picojoules per bit of energy consumption. So this is the highest energy communication scheme, and we're mating that with the wireless power to power the chip. So here's the system architecture. We have a base station, which is located in this gray box. We have a perch where the Dragonfly sits, which is this white square. And then this Petri dish contains fruit flies, which are the prey for the dragonflies. And what we're doing is we're beaming power out of this gray box into the volume above the gray box. The entire experiment takes place in kind of a 1 meter cube volume above that gray box. That's where we're interested in providing power to the system. We have the transmitter and receiver in the gray box, and then power is coming into the Dragonfly by means of the radio frequency signal. So power is coming in at a 900 megahertz carrier. And then that's powering up the DC parts of the chip, and then data is coming back as modulated backscatter on top of that same power carrier. Now, the combination of wireless power and backscatter communication is really nice. The idea behind backscatter communication is you're not running your own oscillator in your wireless device. You're reflecting somebody else's signal. But the good news is, in a wirelessly powered system, we have to supply that signal anyway. So we have to supply a carrier for the purpose of powering up the Dragonfly chip, and as an added bonus, that carrier is available to send the data back from the chip. So it's kind of like chocolate and peanut butter, two good things that taste great together. This is what the chip looks like at a layout perspective. We have a bunch of neural amplifiers, so most of the area in the chip is dedicated to the neural amplifiers or to the sensing task. And then we have a small area of the chip which is allocated to the power rectification and backscatter communication. That's this very small area here. You'll notice, for those of you who do RFICs, there's no inductors, there's no large capacitors, there's no frequency synthesizer block, and so forth. It's a very, very simple system comprised only of power rectification to get the DC power from the incoming RF signal, and then there's a simple FET array which is doing the backscatter modulation. I can show you what that power harvester looks like in schematic form right here. It's a diode ladder. very similar to the RFID tag power harvesters. And you can see that this thing is a nonlinear device in more ways than one. So here's the recovered, unregulated voltage as a function of incident power. And you can see that this is a nonlinear curve. When it's regulated, we sit in regulation at this region beyond about 5 dBm. But the rectifier is a nonlinear element. And then you can see it's also strongly frequency dependent. So we have a good impedance match at 915 megahertz where the carrier is coming in, but if we tried to send in energy at some other frequency, it would be largely reflected by that network. So we see all of those challenges at the same time. We have to match the chip's impedance due to the diodes to 50 ohms to extract power from the antenna. This is what that system looks like in terms of power delivered to the Dragonfly. So as a function of distance, you can see that the voltage available from the rectifier decreases dramatically, right? When we're very close to the perch box, we see very high voltages available from the rectifier, but as we move farther away, or as the Dragonfly moves farther away, the available voltage declines very rapidly. So we have a system that has to be tolerant to orders of magnitude variation in incident power. The chip can't burn out when it's very close to the perch, and it has to run at a very low voltage when it's far away from the perch. And in this case, our chip runs at 1.3 volts as a minimum voltage, which is approaching where the state of the art is. The state of the art would be something on the order of 0.8 volts or so without a DC to DC converter. Some chips can operate at lower voltages, but that's an outstanding challenge. Then finally, here's a bit of information about the angular dependence of the beam. We have a beam that's emitted from the center of that perch box, and you can see that there is plenty of power available toward the center of the beam, but not so much available off the sides of the beam. So that's an antenna design challenge. Trying to distribute the antenna trying to distribute the energy as diffusely as possible over the desired area, and not to waste any energy in areas outside of the desired region. So we've addressed that with a single directional patch antenna in this case, but more complicated approaches are probably promising. This system is exciting from a couple of perspectives. I mean, one is that most of the power in the system is going into the sensing task. About 80% of it actually is going into the sensing task, and communications only consuming about 2% of the total energy. That's an exciting thing. The other exciting thing is that our rectifier efficiency is fairly high. So we're seeing rectifier efficiencies on the order of 20 or 30% at these very low incident power levels, which is pretty good. This is what the chip looks like when it's bonded into its package. You can see the bare die with wire bonds onto the flex that's encapsulated with epoxy to protect it, and then installed on the Dragonfly. The interesting fact is that most of the weight of this device is in the black epoxy encapsulation to protect the chip. So that's the dominant contributor to the weight of the device. Here's just a quick plot showing you the performance of the device. One of the questions that I often get is, well, does the RF signal that you're beaming in order to power up the chip, does that interfere with sampling the very weak signals coming from the neurons? The answer is it doesn't. They're widely enough separated in frequency that the biopotential amplifiers don't respond to the very strong signal that's present for power, and the animals don't seem to notice the presence of the 900 megahertz power signal either. So everybody seems to behave normally. And here's some evidence that the chip is not adversely affected by being wirelessly powered. Here's a neuron that's recorded from a commercial rack. In neuroscience, you usually have very large racks of amplifiers, like relay racks, large racks of many channels set up in an electrophysiology rig. And then we've made a T connection to that neuron and also recorded from our device with wireless power and carrying the data back wirelessly. And you can see that both over the long time scale and looking very close in, they look essentially identical. So the power performance, the noise on the chip, and so forth are dealt with, I think, very, very effectively. So let me try to take us in a slightly different direction and toward a system where we're trying to distribute energy over a wide area. This was a case, in the Dragonfly case, where we have a limited volume of interest where we need to transfer power from the perch box to the animal in flight in some volume. I'd like to next look at the case where you have a mobile device, let's say some sensor, wearable sensor of some kind, that will be moving around in an environment. And this work is on delivering power efficiently over a large area in a building. And we're doing that using MIMO systems. So here's the basic idea. RFID systems, conventional RFID systems, you can think of as kind of a one-to-one relationship between the transmitter or the power source and the wirelessly powered device. And the Dragonfly is an example of this as well. There's a transmitter in the perch box, and there's a Dragonfly chip somewhere out there. So you have kind of this one-to-one correspondence between the transmitter and the wirelessly powered device. We're interested in the case where there are multiple transmitters in the environment. So let's say 4 transmitters that are all potential sources of energy for the wirelessly powered device. And I drew an RFID tag, or I put an image of an RFID tag here, but it could be anything. It doesn't have to be an RFID tag. It could be a power harvester that's driving any type of wireless sensor or device. So what we propose to do is control these transmitters together. And the idea is to somehow jointly optimize the power that is delivered from multiple transmitters in the environment to one or more wirelessly powered devices. And what we'd like to show is that we can selectively boost or deny power to the mobile device by means of this control path right here. So if we control the system in one way, we maximize the power delivered to the wirelessly powered device. If we control in a different way, we minimize the power delivered to the wirelessly powered device. I'm very excited about this, by the way, because it gives us the ability to sell wireless power. In other words, if you're going to have wireless power as a utility, where devices in the environment are powered by ambient sources of energy or transmitters in the environment, you'd like to be able to control those sources in such a way that you can maximize or minimize energy delivered to the mobile device under the control of some system that would let you pay for wireless power as a subscription. So if you pay your subscription fee, I maximize the power delivered to this device. And if you don't pay your subscription fee, I minimize it. That way I can sell wireless power. And we have a way of doing this without measuring the power at the device. And we're making use of backscatter communication to do that. The idea is that in backscatter communication, we send power in from some external device. We selectively reflect energy back from the mobile device, wirelessly powered device, for comms. We can also use that backscatter signal to estimate the channel. And if we can estimate the channel, then we know what that N-port linear network is between all the transmitters in the environment and all the mobile devices in the environment. And we can use that information to control the system. I guess the pithy way to say that is we'd like to rethink MIMO to optimize power delivery, not channel capacity. In some sense, channel capacity is a function of bandwidth and signal-to-noise ratio. Those are not things we care about in the wireless power case. We only care about delivering energy. So it's a similar process, but with a different cost function or a different optimization goal. Not to optimize capacity, but to optimize power delivery. So we've been doing some experiments with this dating back to my time at Duke. This is a photo of one of the office buildings at Duke, or lab buildings at Duke. And you can see we have transmitters scattered around in the environment. So here's a couple of transmitters over here. There's a transmitter over here. There's some around the corner. And then the mobile device in this case is simulated by a cart. And the cart has multiple receiving antennas on it. It has 8 of them. And it has a network analyzer, which is measuring that N-port linear network. And we measure that linear network at a variety of positions of the cart throughout the environment. And in fact, in our experiments, we've surveyed 3,000 different locations of the cart. So we have a picture of what the wireless channel looks like at each of those locations. And that forms a large data set, about 56 gigabytes, that we're going to use to do our optimizations in post-processing. So what we've shown is that we can do optimization of the wireless power transfer in a post-processing experiment, but we also have a way of doing it online. That's something that's ongoing research in our group, is implementing this stuff in real time. Since we have the measurement of the wireless channel at each of those 3,000 positions in the environment, we can better understand the nature of the multipath propagation in the environment. So here what we're going to do is launch a synthetic impulse from a transmitter that's over here and let it propagate through the environment. And you can see, at least in the free space part of the atrium, we've got a nice spherical wavefront, just exactly what you would expect from launching an impulse from an isotropic source. We get a nice spherical wavefront, but then bad things start to happen. We start to see reflection in the environment and reverberation in this open region of the environment. So here is part of the energy being reflected by the elevator doors in this case and reverberating around in the environment. So this is a problem from the perspective of delivering energy consistently or uniformly throughout the space. That multipath propagation causes local maxima and minima in space. That would ordinarily be a problem, but we're trying to turn that problem into an advantage by using knowledge of the channel to control the magnitude of and phase of the signal that's being sent out from each of the 6 transmitters to maximize the energy delivered at a particular point in space. So here's what the system looks like. We've got a set of transmitters distributed throughout the environment and a set of receivers that are co-located with those transmitters but have separate receiving antennas. So energy is transmitted from the transmitters, hits the mobile device. The mobile device uses backscatter communication, and that backscatter communication lets us get an estimate of the channel by measuring the reverse link back at the base station. And in our models, we've assumed that the total power in the system is constrained by safety regulations, for example, by the FCC regulations that we talked about a moment ago. And by doing the channel estimation at the base station, we've dramatically simplified what these mobile devices have to do. So if you think about a Wi-Fi device, they're doing channel state estimation on the mobile device itself, and that is factoring into the way that the channel is optimized. In our case, we're assuming that the mobile devices are very simple. They just simply backscatter some communication link. Hello, I'm here, and by the way, I've paid my wireless power bill. And that information comes back, and in doing that, we're able to estimate the channel at the base station. This is kind of shown here in this block diagram. We've got the transmitter sending energy through some channel that is incident upon the backscatter device. And what we're trying to do is maximize the power delivered to the backscatter device, but we can't measure it directly. It's a hidden variable. That scattered energy goes back through the channel and appears at the receiver of the base station over here. So this is what we observe, and we're trying to maximize or optimize some hidden variable in the system, which is the incident power on the backscatter transponder. So we can cast this as an optimization problem where we're working in the presence of some backscatter gain matrix. This is our matrix of channel state information that we've gathered from the backscatter communication. And we can write expressions for the incident power at the mobile device and the backscatter power received at the receiver. So this is our observable, and this is the hidden variable we'd like to optimize. And so we write that as an optimization problem, and we solve it with one of a variety of different approaches. Any of the algorithms that you're familiar with for optimization could be used. We've done something very simple and just used SVD to solve this problem. Whoa. And this is what that optimization looks like. So here we have the transmitters in blue in the environment, and we have a mobile device in red, which is moving along the orange trajectory through the environment. So we have a mobile device which is going to start here and take this curve walking around through the environment. And what we'll do is we'll plot the incident power at the device in the case where we control the transmitters to minimize the energy delivered to the device. This is kind of like Charlie Brown, a little rain cloud follows him wherever he goes because he's being minimized. And then in this case, this is the guy who paid his wireless power bill. He's going to have maximization, so he's going to get the most power of anybody at his location. So we can let this play, and you'll see the mobile device moving around. Here's the little rain cloud following the guy who didn't pay his wireless power bill. And here is the red hotspot following the guy who did pay up. Okay, so This plot shows the power level that's received in both the maximization and minimization cases. And what we see is the expected MIMO gain, in our case on the order of 8 or 9 dB typically, for the guy who's maximized, and we see nulls for the guy who's minimized. So if you don't pay your wireless power bill, we minimize you and you sit in a null that follows you around everywhere, and that null is usually on the order of 10 or 20 dB deep. And if you do pay your wireless power bill, we optimize in your direction, and you gain by a factor of 9 or 10 or so. So that's what this dynamic optimization is about, and this is, I think, what the promise of MIMO is, that it lets us leverage a concept from communication where we would ordinarily be optimizing for capacity. We can use that same infrastructure to also optimize for power transfer. And then finally, I'll tell you a little bit about some of our work in near-field wireless power transfer, and this is high power, short range. And you can see here that our collaborators are David Smith and Yaroslav Urzumov from Duke University. David and Yaroslav are leaders in the field of metamaterial design, and Jay Lee is at Toyota Research Institute. He's our sponsor in this case, interested in delivering power from some kind of charging surface to a car. There's been a lot of discussion about what form this might take, whether it would be coils embedded in the surface of your driveway that would transfer power to a receiving coil on the chassis of the car, or in an extreme case, perhaps one day we'll have roadways that are lined with transmitting coils, and we charge in motion as the car moves around. I think that the driveway charging case is the more likely one to happen sooner, just because of the enormous cost of deploying transmitting coils around in the environment. So in this case, we're interested in maximizing the efficiency of power transfer from a source coil to a load coil. The source coil, let's say, would be a coil embedded in your driveway, and the load coil would be on the chassis of your car, charging the battery in the electric car. And the way we're going to try to maximize efficiency is by introducing a near-field lens made of a metamaterial structure that I will describe in a moment. And the idea behind the near-field lens is that it couples energy from the source coil, which we'll model as a magnetic dipole, through the lens to the receiving magnetic dipole with enhancement compared to the free space case. So what's happening is that the magnetic field is being drawn through the metamaterial lens and then focused to a point out at some distance d, which is where the car is. I think as a practical case, what you would do is have d be the distance between the roadway and the undercarriage of the car, and then you would perhaps bury the transmitting coil a distance d below the surface of the ground. So this metamaterial lens would be at the surface of the road. And Yaroslav has done some theoretical work with a dipole-dipole coupling model showing that a magnetic superlens, which is just simply a structure of mu equals -1, can focus the incident magnetic field at a particular distance. And so here are a couple of different cases where we show a significant gain in efficiency at a particular distance. This is what the metamaterial structure looks like. It's an array of coils, a 3D array of coils that are kind of made like a wine crate. And they have a resonant frequency that's chosen so that the effective permeability of that material is -1 in our frequency range of interest. And we were aiming for operation around 13.56 megahertz, or right here. And you can see that this metamaterial structure ends up having mu equals -1 right in that band. That's shown here in this blue plot. Okay, so it's a 3D structure formed of many coils made of copper conductors on a dielectric. And that is the structure that forms the lens. And this graph shows theory and experiment. So here is a set of plots showing the the theory here in blue. This is enhancement versus air. So the blue plot shows a coupling efficiency, let's say, of about minus 45 dB relative to air of minus 55 dB. So we see about a 10x improvement in theory. And in measurement, we see somewhat less than that. We see somewhere around 8 or 9 dB, maybe 10 dB at the max. And what's interesting about this is the metamaterial lens is a lossy structure, right? It's comprised of lossy copper with some resistivity and dielectric material, which has some losses as well. But the focusing effect dominates over the losses in the material to give us a net improvement in efficiency. So we see an enhancement on the order of 10 dB over free space, including all of the losses in the material. I guess I'll conclude by giving you some kind of concluding thoughts here. First thing I'd point out is that wireless power is an interdisciplinary subject. There's work in electromagnetics in terms of the coupling from a source to a load antenna of any kind. There's antenna work, there's circuit work, and analog and digital control work as well. All of these systems that we've described have some contribution from each of these different areas. For certain applications, I think that wireless power is basically here today. There are 6 billion RFID tags made each year. So that's 6 billion tiny wireless computers being produced at all the time, continuously. I think that the vehicle charging application is next. There's a lot of demand for wireless charging of electric vehicles, and it's a technology for which there is an approach. Right? There is a technology that can solve that problem, which is that near-field magnetic coupling, perhaps with a metamaterial lens to enhance the efficiency. I guess my last point would be that Tesla's dream of worldwide wireless power transfer to completely eliminate the wires seems just as far off today as it did in the 19th century. There isn't a technology that will address that dream. So there's ongoing research needed in that area. So with that, I'd like to thank all of my students and postdocs and collaborators and sponsors. And thank you for your time in listening to me, and I'm happy to answer a few questions.
We can entertain only about 1 to 2 questions because Matt has to go to his class to teach. So, question? Yes?
So can the metamaterial lens increase the efficiency also at the lower gap distances where the efficiency is higher in free space?
Sure. So the question is, can the metamaterial lens improve efficiency at low gap sizes? The answer is probably no. So there is a region of distances where the gain from the near field focusing exceeds the losses in the materials. And that's shown here. This spatial regime is where the metamaterial is a net win. Where the source and the load are closer together up here, the metamaterial is probably a net lose because the material losses will dominate. So it's useful at larger separations of several times the coil diameter. That's a great question. Yes, Payman.
So suppose I haven't paid my power bill. Can I just follow somebody who has?
Sure. So Payman's question is a great one. Can I tailgate someone who has paid their power bill? Well, the answer comes down to the coherence distance of the channel, right? So if you're following somebody within the coherence distance of the channel, you'll be in electromagnetically the same environment as the guy who's paid his bill. It turns out that the coherence distance in the channels that we've measured in this frequency range is sub-meter. Right? So it's on the order of centimeters. So you'd really have to tailgate somebody at an uncomfortable distance. Yep. That's a great question.
A related question to Payman's question. It sounds like the amplitude and phase of your MIMO antennas or transmitters is a solution to the optimization problem of how to deliver maximum and minimum. How did the number of transmitters scale as the number of subscribers scale with varying degrees of payment, so to speak?
Sure. So your question, Visvesh, is mostly about what's the scalability of the MIMO WPT system? Yeah. I think that really it's a very complicated question because it comes down to the kind of density of people or density of mobile devices you expect in the region around each transmitter. We have some partial answer to this that we've worked out for uniformly distributed mobile devices, but I don't really think that's the realistic case. In other words, I don't expect that mobile devices will be distributed on a regular grid, but we've done the math on that, and I don't recall the precise numbers, but we have treated that case. The more likely case is that the mobile devices will be bunched up together, because people have kind of a natural traffic flow if they're carrying the mobile devices around. That'll be a more complex question.
All right. We really have to stop because Matt has to go to his class to teach. Let's give Matt another big hand.
Thank you.